Hello, I'm José Proença from the University of Porto in Portugal, and I'm here to present you Lince, which is a tool to simulate and analyze hybrid programs. This is a hands-on tutorial where I'll explain slowly what are hybrid programs and what can Lince do for you. And Lince, if you want to try it at home, you just need to go to the website here, LMFDI Human PT Lince 2.0, and you'll be able to see the latest version of Lince running in your browser, without any server required. So, first of all, Lince is supposed to analyze hybrid programs. What are hybrid programs? Hybrid programs combine two kinds of programs, the traditional discrete programs that look like C. We have variables that update, while loops, if then else's, and so on. And you have some continuous part. For example, here we say that the derivative of the velocity is minus 9.8. The derivative of P is given by V. This is with respect to an implicit variable for time. And now the goal is to be able to put both of them inside the same program. And what you see in the middle here is a hybrid program, where we initialize P and V to 0 and to 2 respectively, and do an infinite loop while true. We keep on checking if velocity is small or equal than 10, and if that's the case, we evolve P and V according to these differential equations for 1 second. Otherwise, we evolve using this system of differential equations for 1 second. And the difference here is the derivative of the velocity is either 5, meaning we are accelerating, or it's minus 2, meaning we are braking with a lower absolute value. So this is supposed to mimic a cruise control. We are trying to keep the velocity stable around 10. And we also want to introduce more things. So I also introduce later things like uncertainty, be able to say our velocity, initial velocity is actually random from some uniform distribution, or we want to say let's validate monitors. For example, say that every 2 seconds we check if position is small or equal than 12. The monitors part is not implemented, the randomness is already implemented in the current version, but these are still ongoing experiments. So if you open Lince, what you'll see is a window or a widget where you can introduce your hybrid program. You press go and you'll produce you a plot. A plot you can navigate, traverse, point your mouse and try to obtain the values. And we're going to go into this very soon. In this case, we have a cruise control, and you can see that every second the velocity updates or continues based on the need to accelerate or brake. And you can see there's some curves being modeled by the position that after 6 seconds reach around 70 in the end. So that's the kind of things that Lince can do for you. But before I go to the demo, I want to just clarify why do we care about Lince? Because there are many tools for these kind of things. The first thing is it's very easy to start using. You don't need to install any hard software, just need to open a website. It does not even require a server to run, meaning everything is compiled into JavaScript. You draw your program here, you say reload, and suddenly you have your plot being plotted. And there are a few more things you can do, but you're going to see a bit later. The language is very simple. It's a minimalistic C-like language, so you don't need to depend on workflow language combinations of more complex concepts, so it's meant to be as simple as possible. Also meaning that the semantic is very precise. So we have papers where we present the precise semantics of this lightweight model, and you can specify it very, very clearly what does it mean to execute this in theory. Furthermore, because this is relatively simple, meaning we can experiment with new extensions like the monitors or the randomness we saw before, and we can involve master students, PhD students, industrial partners, and so on during our efforts to improve or choose which feature should be part of this. So, going back, I'm going to now jump into this website, and the thing you're going to see, I'll open a different tab, is this. You see a cruise control. Here you have some way of configuring the plot, saying I just want until 5. I can change this to 7 and saying reload, and you see everything adapts here. And you have here our cruise control. Instead of 10, if you want to model 20, Shift Enter also updates, or if it's every 2 seconds, you can also change this and say Shift Enter, and you have the new plot, which is the same in this case. So you can quickly experiment and play with this. So, but before we go, let's start with the basics of the basics. So we're going to go into the basic. So you turn on and off, you turn different examples. The most simple example we have here is the accelerate, where you set variables to 0 and have a single system of differential equations. With this system, you see the position P evolving until 0.5, which means it reaches the point 25 after 5 seconds. And the velocity here is linear and reaches the point 10. So this is the very simple example. You can have more complex examples like x derivative given by y and y derivative by minus x, and this will produce you a single continuous function that corresponds to a wave. And this is for 10 seconds. So more examples include the composition. So this is now a real hybrid program. While the other one was purely continuous program, now we say we have two different systems, the one that accelerates and one that brakes. And we do this for 5 seconds. Or if you prefer, the next one will be for 4 seconds. We have a different model. So now we are modeling indeed multiple differential equations. We can even break halfway and say, at this point, I want to reset my P to become 0. I reload, and you see at some point there's a break, a discontinuity, and then you can proceed. So this gives you really the freedom of combining differential equations entangled with what the discrete program is actually doing. And there are more examples you can experiment. Now I'll proceed with a variation of our cruise control. We've seen this cruise control before. I'm going to go into the probabilistic versions, and I'm going to see a variation of this cruise control. First of all, without probabilities, meaning this adaptive cruise control. Adaptive because the goal now is not to keep a given velocity, but to try to keep the distance to the leader car. We have two cars. The leader starts at this position, 50, at this velocity, 10. The follower, the one in the back, the one I'm controlling, starts at position and velocity 0. We require acceleration of the leader to be 0 because we have the same kind of, the same while loop we had before, except here we have a condition that checks if it's safe to accelerate or not, which is more sophisticated than velocity smaller or equal than 10. So this we manually compute it, and now we want to experiment if it works or not. Here we chose 2 and minus 2 as the velocities, the accelerations for our car that's following, and now we say, well, let's say what happens if you eject actually a bit lower, slower, 2. Understand, okay, this will actually break our system. And now we can also say the car will now be braking. Understand, braking does not work. But if the car is accelerating, everything is fine. So we can start experimenting here. We're filtering our plots to only care about the p variables, because if you comment out this line, you'll see we have a bunch more variables here that you can turn on and off. So you can hide the probabilities, the positions, and you see the evolution of the velocity as well. And now we're going to use a different variation that behaves better with accelerations which are different from one. And that's the version I have here. Sorry, not here, but this one here. This more complex version has even more complex safety function that it checks if it's allowed or not to brake or to accelerate. Everything else is very similar. We can play now with the acceleration of the leader, which is a bit more hiding here. We know if it's 1, this is the behavior. If it's 2, that's the behavior. If you have minus 1, you see a different behavior. And you see the position of the car going back and forward, trying to keep the distance to the car in front. So let's roll back. We have our simple example, and now let's experiment with probabilities. The probabilistic version is here, where the main difference is saying every time the car in the back, the car in front, I mean, the leader, we're going to choose a random acceleration between minus 1 and 1. And if you try to run this while commenting the seed, because the seed fixes the randomness, and I run this multiple times, you see that sometimes everything looks okay, but it might actually go overboard. There was an example that seemed to go overboard. So it's not really clear if this will actually work or not with acceleration. It's not meant to work, but you don't know for sure. So what you can do here, for example, is say, I want to run multiple times, for example, 10 times. And you can have multiple simulations being displayed. Of course, this overlay clutters the view and makes it very hard to see. Therefore, there's a functionality that only exists currently in the older version of Lince. By the way, the older version of Lince can be accessed by looking here at the predecessor of Lince, which is less organized code. It has a bit more features, but is not so well polished as the current version. And if you go to the older version, we have the variation of our adaptive cruise control, the version with acceleration which is random, and now we say we want a different plot. We want to plot a histogram. Every 1 second check this property and plot it. And you can do this, in this case, for 50 simulations, for 40 simulations, and run again. We run for 50, you run again, and you see that sometimes you have different results. You can even say, I want to query the probability of this being true by sampling this interval 30 times. In this case, it assumes around 7%. If you run it, sometimes has bigger number, sometimes lower number. I'm running it again, and obtain now a 3%, so it's a relatively low value for this probability. So before I finish, I want just to show you that they also have debug functionality, like the ones used for monitors. Right now, we're only trying to export possible traces. For each possible point, we try to say what are the current values, and this can be used to be fed into different tools that are doing offline monitoring or so. So this was in a nutshell. Lince, I hope I gave you some help, and please feel free to try the tool by yourself. Bye-bye.